So good evening everyone. So welcome to the first workshop of OSCILLION, which will comprise of the topics of circuit analysis and introduction to Laplace Transform. Before that, let me give you a brief introduction of myself. I am Shomesh Lairi Chakrabarti, MTech first year in Power Systems. And so without further ado, let us start the workshop. So basically, we know that what is analog electronics. Actually, analog, what does analog mean? Analog is anything which is continuous in nature. So basically, like in nature we can find the natural waves, sound waves, etc. Everything is analog in nature. Analog electronics are electronic systems which are continuously varying with varying signal, whereas digital signals are those which basically take two values only, either 0 or 1. Analog waves can take any value depending on the nature of the signal. Like in this example, you can see there is a peak to peak 10 voltage of analog signal, and also there is a digital signal which has a 0 value and the maximum value of 5 volt. The digital value takes either a 0 value or 1 value which is corresponding to 5 volt. So now we come to the RC circuits. Actually, if you know that in the fan we use or in the cameras we use, everything consists of RC circuits because of the ability of the capacitor to hold charge. So these circuits are containing both resistance and capacitance. The RC circuit is basically used in camera flashes, as I just mentioned, pacemaker, timing circuits, etc. Now there is an intrinsic property of a capacitor that it doesn't allow any sudden change of voltage across it. So in the left diagram you can see that that initially the capacitor is uncharged. So as soon as we close the switch at t equal to 0, the capacitor will still be that is Vc 0 minus is 0, so Vc 0 plus will also be 0. So the capacitor will be short circuited when we close the switch. That means the current flowing through the circuit will be Vs by R. Now as t tends to infinity, we know that the capacitor will behave like an open circuit. Therefore there will be no current flowing through the circuit, and the entire source voltage will appear across the capacitor. And if you go to the next slide, this is the source picture of an RC charging circuit. So Vs, if you write the KVL equation, Vs equal to RC dVdt plus Vct, where Vct is the charge voltage across the capacitor. Now upon solving this differential equation, you can get the equation of the voltage across the capacitor, which is given as Vs 1 minus e to the power minus t by tau. Tau here is RC, which is the time constant of the circuit. Now if you can see what I just mentioned, if you put t equal to 0, we will get Vc equal to 0. This is because, as I said, capacitor will be short circuited when we are just switching the circuit. And if you put t equal to infinity, you will get Vc equal to Vs, or the entire source voltage will appear across the capacitor. Similarly, for the current across the capacitor, you will get the equation of Isc equal to Vs by R e to the power minus t by tau. So also from the curve you can see that the charge capacitor voltage is an exponential rise, whereas the capacitor current is exponential drop in nature. Now similarly, for an RC discharging circuit, the same thing can take place. If you write the KVL equation, you will get Vct plus Rict equal to 0. Upon solving, you will get the Vc equal to Vs e to the power minus t by Rc, and Ic equal to Vs by R e to the power minus t by Rc. Notable is that as t tends to infinity, both current and voltage will tend to 0. This is because this is a source free circuit. There is no independent source in this circuit, and these are the curves given as, again, which are exponential fall in nature. And this is a simulation done in the PSCAD environment. As you can see that we have taken an simple RC circuit where the resistance value is 1 ohm and the capacitor value is 0.01 farad, and the source is an ideal voltage source. Now we are measuring the capacitor current as is given by IC, and we are also measuring the voltage across the capacitor. As I just said, that the capacitor voltage will be an exponential rise in nature, you can see from the left curve, and also the capacitor current will be decreasing exponentially, which is given by the right curve. So this is done in the PSCAD environment. And now we move next to the RL circuits. So RL circuits are those which consist of resistance and inductors in series. What is an inductor? Inductor is basically just a coil. Inductor is just a coil which has a value of some which is wound upon itself. The instant the switch is closed, the current begins to flow and is opposed by the EMF induced in the inductor as per as Lenz's law. Now an inductor has an intrinsic property that it doesn't allow sudden change in current. Just like a capacitor doesn't allow sudden change in voltage across it, an inductor will not allow any sudden change of current. Therefore, if we go to the charging circuit, as soon as the charge is closed, as soon as the switch is closed, the inductor will not allow any sudden change of current. Therefore, it will behave, the inductor will behave as an open circuit. That is why the entire voltage will appear across the inductor and the current will be 0. However, as the time progresses, as t tends to infinity, we know that VL equal to L di dt. So as t tends to infinity, VL tends to 0, or the inductor will be short circuited and the current will be flowing through the circuit will be Vs by R. So accordingly, you can see that ILT equal to Vs by R, 1 minus e to the power minus t by tau. Tau here is given by L by R, which is the time constant of the circuit. If you put t equal to 0, you can see that the current will be given by Vs by R, which is the current will be 0, as the inductor will not allow any change of current, and as t tends to infinity, the current is given by VL by R, as the inductor is short circuited. Similarly, the voltage across the inductor is given by VL e to the power minus TR by L, or T by tau, L by R, where tau is L by R. Similarly, RL discharging circuit, there is no source in this case. Therefore, the inductor voltage and the drop across the resistance will balance each other as far as KVL. So VL is given by L di dt, as you know, and this is the KVL equation. Upon solving, you can get that IL will be Vs by R e power minus t by tau, and VL will be Vs e power minus t by tau. This is because they are also exponentially decreasing in nature. This thing will be more clear if we go to the next slide. So here we have simulated another RL circuit, where it is there is an ideal voltage source with a 10 ohm resistance and a 0.1 Henry inductor. Now you can see that the inductor voltage is exponentially decreasing in nature. At t equal to 0, it gives the maximum voltage, and as t tends to infinity, it becomes almost 0, because the inductor becomes short circuited in steady state, and also the inductor current is given by the exponential rise in nature. So this is again done in the PSCAT environment. Now we'll come to AC circuits. Now everything nowadays is done by AC circuits. This is because alternating current has some distinct advantages over the direct current. Alternating current or AC circuits are simple circuits that are powered by an alternating source. This can be, like in India we have the 50 Hz frequency source, and in America or US you have the 60 Hz source. So the main passive components employed in any circuit, you know, are the capacitor, resistor and the inductor. These three passive components have one feature in common: they limit the electrical current rate, because they offer certain kind of resistance. The resistance that is offered by the inductor or capacitor is often called as reactance. If the current passes, the alternating current is alternating in nature as it goes back and forth, as it is underlined here. As they offer an impedance inside a circuit, passive components in AC circuits act quite differently compared to those in the DC circuits. So you can see here there is an AC source connected with a DC bulb, with a load which is a bulb, and the AC waveform is given here. Now we have connected a simple resistor to an AC source. Now the source voltage here is V equal to V naught sine omega t. Most AC voltage sources are taken as a sine function. So since resistance is a simple passive element, so the current voltage relation will be given by I equal to V by R. Now since hence you can get I equal to I naught sine omega t, where I naught is given by V naught by R. Now you can see that since there is no voltage phase difference between the voltage across the resistor and the current flowing through the resistor. Thus these two components are completely in phase with each other, as it is given by this graph here. So the phase difference here is basically 0. Now we have a AC circuit with a capacitor only. Now the capacitor voltage, you know, is given by V equal to Q by C. Therefore Q equal to, where V is the source voltage, is a sinusoid function again. Therefore I equal to dq dt, you know, and where Q is equal to C V naught sine omega t, you differentiate it with respect to time, and you can get that I equal to omega C V naught cos omega t. Omega is the frequency at which the source is operating, which is 2 pi f. F is 50 Hz. C is the capacitor which is used. V naught is the peak value of the sinusoid function. And so now the current through the capacitor is actually leading the voltage. You can see that I equal to I naught sine omega t plus 90 degree, whereas V is V naught sine omega t. Thus the current through the capacitor is always leading the voltage by an angle of 90 degree. here one thing to note is that the x I naught equal to V naught by xc, where xc is the capacitive reactance, which is given by 1 by omega c. This is because when a capacitor is connected in an AC circuit, you need to calculate the impedance that is, or the reactance that is offered by the capacitor, which is given by the formula x equal to 1 by 2 pi fc, or x equal to 1 by omega c. So the current leads voltage by 90 degree in case of a capacitive circuit with pure capacitor. Now we have a pure inductor. Now we know that the voltage across the inductor is given by the empirical formula VL equal to L di dt. Here VL is V naught sin omega t, which is the applied source voltage. So di dt equal to V naught by L sin omega t, and if you find the value of I by integrating, you can get I equal to I naught sin omega t minus 90 degree. In this case, what is happening? The current through the inductor is lagging the applied voltage by 90 degree. So, and here also you can see that the XL is the inductive reactance similar to the capacitive reactance. However, in this case, XL is given by the formula of omega L, XL equal to omega L or 2 pi FL. Now the phase difference between current and voltage in this case is minus 90 degree, or the current or voltage leads the current by 90 degree. So this is an RLC series circuit. VR is the voltage drop across the resistor, VL is that across the inductor, and VC is that across the capacitor. Now if you want to solve this, you can do this by taking the KVL directly and solving the differential equations. However, you will get a second order differential equation in this case, which is kind of hectic to solve. In those cases, we take the help of Laplace transform by converting it into the S domain. Now there is one empirical relation here with the impedance and the circuit elements. You can see that the resistor is always given as R angle 0 degree, whereas for inductor the reactance is omega L, which is taken to be j omega L, where j is an imaginary number, as you know, and j can be written as 1 angle 90 degree. Therefore ZL can be represented as omega L angle of plus 90 degree. Similarly, for capacitor, 1 by omega c can also be taken as 1 by j omega c. So you multiply both numerator and denominator by j, you will get minus j by omega c. So minus j can be written as minus 90 degree. So it's given by 1 by omega c angle minus 90 degree. These are the phasor diagrams for the RLC circuit. You can see for the resistance, voltage across the resistance and current are in phase with each other. Similarly, for the inductor, voltage across the inductor leads the current through it by 90 degree, and for capacitor, the current through the capacitor leads the voltage across it by 90 degree. Now when we are combining it in a series RLC circuit, now VL and VC will be in phase opposition to each other, as you can see here, and VR and I are completely in phase. So the resultant formed will be along the direction of Vs. Vs is the resultant of VR plus VL minus VC. We have to keep in mind that here we have taken that the inductive voltage drop is greater than the capacitive voltage drop. Now moving on to the next slide. So from phasor diagram, from the previous phasor diagram, you can see that Vs will be equal to mod of VR plus VL minus VC. So if you take the mod on both sides, we will get Vs equal to VR square plus VL minus VC square. Simple phasor formulas. Now the same current is passing through both inductor, resistor and capacitor, since it's a series circuit. So VR will be given as IR, VL will be given as I into XL. XL is the inductive reactance, and VC will be given as I into XC. Now XL equal to, now we have just defined XL equal to omega L and X equal to 1 by omega C. Therefore Vs, you can get the equation Vs, putting these values here, we can get Vs equal to IR square, putting the value of VR, VL and VC, and finally you can get the value of Z, where Z is defined as the impedance of the circuit, or the effective resistance that the current faces when it's passing through the circuit elements. Now if we and from the phasor diagram, you can see that R is in phase with the current, XL and XC are in phase opposition. XL leads R by 90 degree, XC lags R by 90 degree, and Z is given as the resultant of R and XL minus XC. And the phase angle will be given by XL minus XC by R, where provided that we are taking that the inductive reactance is greater than the capacitive reactance. If the reverse was the case, then it would have been XC minus XL by R, and cos phi is the power factor of the circuit, which is given by R by Z. Now this is another simulation done in the PSCAD environment. We have taken the RLC series circuit, where R is given as 50 ohms, L is given as 0.001 Henry, and the capacitor is 0.01 farad. We are measuring the voltage drops across the inductor and the capacitor, and the current through the circuit, which is the series current flowing through the series circuit. The source is a non-ideal source. It has a source resistance of 1 ohm. Now as you can see from the curve, the blue curve indicates the series current, and you can see that the voltage across the inductor is actually leading the voltage across the inductor is leading the series current, because you can see that the green curve takes its peak before the blue curve is taking its peak. Therefore the voltage across the inductor is leading the series current. Similarly, the voltage across the capacitor is lagging the series current, because it's the capacity voltage taking its peak after the series current, therefore it's lagging the series current. So this response shows that how the voltage across the inductor and capacitor are related with the series current. Now you should remember one thing, that why is it not being exact, like why is the voltage across the inductor not exactly 90° leading through the current, or why is the voltage or capacitor is not 90° lagging through the current? This is because this is a RLC series circuit. So in this case we have to calculate the phase angle, and these waveforms are lagging or leading each other by exactly the phase angle value, which is just showed is tan inverse of XL minus XC by R. So this thing shows the waveform, output waveform. And so now we go to the topics of Laplace transform. Any doubts, anyone? Any question? Yes.
Hello. So you get the basic property of the capacitor. Up now come to the inductor. So what will be the effective impedance? XL equal to J into omega L, right? Omega equal to 2 pi F, where F is the frequency of the supply voltage, or whatever will the supply, right? So again, if we are considering voltage across the inductor as VL, so we know the property of the inductor that current lags 90° with the voltage across that inductor. So we are considering voltage VL. So now current across the inductor will be like this one, 90° lag. Now come across the resistor. If we are considering voltage across the resistor is VR, then we know that property of the resistor is as current and voltage are in the same phase. So current will be also like this, IR and VR. You got the point? Now we combine all these three elements as series or parallel. So what we have to remember that we just see the voltage across that element and current across that element, and then we consider what is the phase angle, and then we get the phasor diagram of the entire circuit. Then we vector means vector से हम लोग we will sum that everything. So this one is the complex means inductor or capacitor complex उसको this one is indicating the plus 90 degree, 190 degree. Okay, so if we take the this is the RLC series circuit. Okay, so what is the common in between all the three element? Current. So whatever means a trick to draw the phasor diagram is whatever is the common, take that means that parameter as the reference. So here current in all the three elements are the same, so we will consider current as the reference. Okay, so take current as the reference I. Now the voltage across the resistor will be how much it will be? V equal to IR, and we know that current and voltage across the resistor are in the same phase. So a current same current is flowing through all the three elements. So if we consider that voltage across the resistor is VR equal to IR in the same phase. Okay, now come across the inductor. Voltage across the inductor will lead 90 degree from the current flowing through that inductor. So current flowing through that inductor is I. So voltage across the inductor will lead 90 degree from the current flowing through that element. So 90 degree lead. This one will be the voltage across the suppose VL. Have you got the point? Now come across the capacitor. Voltage across the capacitor will lag 90 degree from the current through the capacitor. So current through the capacitor is I. So voltage will lag how much? 90 degree. So this will be the voltage across the capacitor. Now means both are just phase reversal, 180 degree phase. So we can algebraic add or subtract, right? So it depends upon the means magnitude of the impedance. If suppose x the capacitance value dominates with the value of inductor, then this amount will be higher than this one. If inductor will be larger, then this will dominate, right? So effective we are considering that VL is greater than VLC. So VL minus VC effective, this one will be the effective VL minus VC. Now add both of them. So this was VR and this is the effective voltage across these two elements, VL minus VC. So add both of them, you will get the resultant voltage V net, and V net will be equal to source voltage. Same if we will have to draw the phasor diagram of the parallel RLC circuit where voltage will be the equal across, because we know that in parallel circuit voltage is the same, current got divided. So where means there I will have to choose voltage as the reference phasor. Okay, from there we will see just as I have seen in the RLC series circuit means voltage current across the each element, and voltage by the property that whether it 90 degree leads or 90 degree lags or in the same phase. Accordingly, we will draw for the parallel RLC circuit. You have to do this, right? You will do. It's your homework. You can do that one. Okay. One more thing. Suppose initially we had Somesh have explained the DC analysis, right? So why we are doing DC analysis, AC analysis? Because all the circuits basically contains some of the basic elements: resistor, diode, inductor, capacitor, voltage source, and switches. With these all these basic element, you can draw any circuit, whatever be the circuit required in the our world, whatever the component are running, just need all these element. If we know the basic property of all these element, we can solve any type of question. So our problem arises where that we are not analyzing the basic element. If we analyze the basic element property, then we can solve any type of question. That's why we are moving towards the coding and not towards the electrical engineering. Main problem is there that we are not getting the basic property, right? So suppose there is a capacitor, there is an inductor. So but we see that x equal to 1 by j omega c, xl equal to omega l. So if you have read the basic network in your first semester or third semester, whatever, so where you have seen that sir for DC analysis, sir short circuit the inductor, for steady state, and for open circuit the capacitor. Because what in DC analysis we frequency equal to 0, okay. So omega equal to 2 pi f equal to 0. So for a steady state, x equal to whatever 1 by tends to 0, tends to infinity. So if any impedance tends to infinite value, means they are offering high impedance to the current. They are not allowing to follow the flow current through them. So we assume that in a steady state that capacitor is converted into the open circuit. Now come to the inductor. For inductor, XL equal to 0 into L equal to 0. So if any element is offering zero impedance through them, then what we will consider that element as a short circuit. If impedance equal to 0 means circuit we can assume as a short circuit. So in a steady state analysis for DC source we assume inductor as a short circuit. So we just convert inductor as a short circuit in our network analysis. Okay. Now two more thing. Inductor does not allow sudden change of current and capacitor does not allow sudden change of voltage. So we are trying to analyze why it is happening, right? So we know the expression IC equal to C dVc by dt, right? C dVc by dt. For sudden change of current, time tends to 0. Sudden change means what we are assuming? Sudden means considering in 0 time interval, right? For 0 time interval, if 0 is in denominator, we will consider IC as a infinite, okay, and for V equal to L di by dt. For sudden change, voltage will tends to infinity. Sudden change means what we are considering? Time as a 0 interval. So this is the reason why capacitor does not allow sudden change of current and sorry galat. This is the reason why means for the capacitor does not allow sudden change of voltage across them, and inductor does not allow sudden change of current across them. So anywhere if we consider that to limit the current across the element, so what element we will prefer? We will prefer their inductor to limit the amount of sudden जैसे कहीं भी हम फिल्टर का डिज़ाइन कर रहे हैं, कोई भी फिल्टर का डिज़ाइन कर रहे हैं जहाँ पे हमको क्या कर रहा है, जैसे पीक आता है करंट का, वी डोंट नो दैट नॉइज और समथिंग इन द सर्किट, सो वेयर वी यूज इंडक्टर so that will try to limit the peak surge of that current and save our provide protection to our circuit, right? हाँ हाँ नहीं तो शुरू में जैसे हम अभी सर्किट का एनालिसिस करेंगे जो कोई भी आप जैसे क्या बोलते हो कैपेसिटर सडन चेंज ऑफ वोल्टेज अलाउ नहीं करता है ना, तो आप अगर कैपेसिटर के अक्रॉस वोल्टेज लगा रहे हो तो जो उसका पिछला वाला प्रॉपर्टी है, जैसे कैपेसिटर ने कुछ वोल्टेज, अभी पंखा चल रहा है ठीक है, तो कैपेसिटर में कुछ वोल्टेज या कोई भी मतलब चार्ज हो रखा होगा उसमें, तो आप अगर डीसी वोल्टेज या कोई भी दूसरा वोल्टेज सोर्स आप अप्लाई कर रहे हो तो वो अपने पुराने वाले प्रॉपर्टी को कुछ देर कंटेन करेगा, फिर धीरे धीरे जब उसकी वो प्रॉपर्टी ख़त्म हो जाएगी फिर जाके स्टेडी स्टेट, मतलब हम क्या बोलते हैं, दो स्टेट बोला जाता है, एक ट्रांजिएंट स्टेट और एक स्टेडी स्टेट। स्टेडी स्टेट ट्रांजिएंट मतलब तुरंत सडन चेंज, जो हम देख रहे हैं कि तुरंत क्या क्या चेंजेस आ रही है सर्किट में, जबकि स्टेडी स्टेट में हम एक देख रहे हैं कि जब सब कुछ स्टेबल हो जा रहा है, एक टाइम कांस्टेंट, जैसे हम किसी भी सर्किट का स्टेडी स्टेट के लिए क्या मानते हैं, 5 टाइम कांस्टेंट, तो उसके बाद हम देख रहे हैं कि तब जाके तो स्टेडी स्टेट एनालिसिस में हम इसको क्या कर देते हैं, ओपन सर्किट कर देते हैं, और इसको स्टेडी स्टेट एनालिसिस में शॉर्ट सर्किट कर देते हैं। तो इसीलिए आप जब अभी आप पढ़े होंगे या ना पढ़े होंगे, when we will analyze the network analysis of RL circuit or RC circuit, for RL circuit you will consider IL0 minus equal to IL0 equal to IL0 plus. What is the meaning of this one? That just before t equal to 0 instant, current through the inductor will be same as the current just after 0 instant. Okay, means it is showing that inductor is not allowing sudden change of current. Similarly in capacitor we just write Vc0 minus equal to Vc0 equal to Vc0 plus. So it is showing that capacitor does not allow sudden change of voltage. Are you getting my point?
What is the meaning of IC is infinity? What it tells that IC infinity is something?
Suppose for means we are considering I have got your point why I am considering IC as an infinity, right? So for sudden we can consider time interval as a 0, right? 0 interval, very small. In that interval, if we consider, then IC will tends to infinity because t tends to 0. For that infinity current, we require infinity amount of voltage across the capacitor, right? That's the reason means capacitor does not allow, because we are not supplying infinite amount of voltage across the capacitor. Okay. Continue.
सर ये माइक से ही बोलते एक्सप्लेन कर। Thank you, Akhil. So you know, as Akhil just drew this phasor diagram, this is VR, this is I because voltage across the resistor and the current across the resistor in series, and this is VL and this is VXC. This is the resultant. Now you can see that the series current is given by the blue curve. Okay. Now since the inductor voltage will always lead the series current by an angle given by phi equal to tan inverse XL minus XC by R. That is why the voltage across the inductor in this case is actually leading the current. You can see that. And similarly, the current voltage across the capacitor will lag the series current, because voltage across capacitor normally lags the current. Now one question I have: suppose VL and VC are equal, what will happen in that case? Right. So in that case, VL equal to VC. That means F equal to 1 by 2 pi root LC. This is given as the resonating frequency. In that case, the circuit completely becomes a resistive circuit, and the current rises abnormally because it is not further limited by the reactive capacitive reactance or the inductive reactance. So I hope your doubt is clear. So you go next to Laplace transform. So basically, why do we use Laplace transform? Laplace transform is actually a very powerful tool which we basically use to solve certain differential equations. We have in electrical, you often encounter differential equations like the RLC circuit or the normal series RL circuit. All those are made up of differential equations, and often if the number of circuit elements are more, the order of the differential equation similarly increases. In order to solve this, we use the Laplace transform, which converts the differential equation into a kind of algebraic equation, as we will see just now. So how do you construct a Laplace transform? Basically, you construct a Laplace transform by going from the time domain to a domain which is called the S domain. You do this by Laplace transform. Suppose ft, you have a function of ft. Ft is any signal. Say ft is a unit signal. Say ut. Everybody knows what is ut, unit step function. Unit step function is given like this. This is the time. This is ft. You will get a unit step function. Unit step function is given as 1 when t greater than 0, greater than equal to 0, and 0 when t less than 0. So you can see that while for time less than 0 the function is 0, and for time greater than 0 it is given by 1. This is called the unit step function. So suppose you have this function, you want to convert it into the Laplace domain. So how do you do it? You just take that function, multiply with a factor e to the power minus st, and integrate it between 0 to infinity. Now why we are doing this? We are taking it into the Laplace domain because certain mathematical calculations become easier in the S domain compared to the time domain. Now this S is basically a complex number. It is given by sigma plus j omega. Sigma is the real part, omega is the imaginary part. So you can write the Laplace S domain like this. This is the S domain. By sigma you have the real part and j omega is the imaginary part. So you can convert any given signal into the Laplace transform provided certain Dirichlet conditions hold. Like it should be piecewise continuous and it should not be exponentially to increasing in nature. Means it should be piecewise continuous, means over an interval the function has to be continuous. Now going to the next one. Why do you use Laplace transform? It converts the differential equations in time domain to algebraic equations in S domain. Because often you encounter with differential equations that are in the order of 3 or 4. Laplace transform reduces that load of the burden of calculating all such things and converts it into a simple of algebraic equation. Now often we have a problem that circuits in the time domain cannot be simplified. As we have a problem next, we can see that with that problem is done in the S domain. We need to use several differential equations in that case. Suppose we have a R, L, C, everything is mixed, then in that case the circuit becomes extremely complex. In those cases we use the help of Laplace transform. So here is an example. Say we have, just as I said, the unit step function ut equal to 1. So suppose we are taking in this case the example of the unit step function. So in this case ft will be given as 1 e to the power minus st dt. So so this is basically 1 into e to the power minus st. It will be given as e to the power minus st by minus s, limits over 0 to infinity. So 1 by s. So as I am converting it into 1 by s, the limits will be converted from 0 to infinity. The lower limit will be infinity and upper limit will be 0. So 1 by s, as I put 0, it will be 1, and e to the power minus infinity will be 0. So this is given as 1 by s. So the Laplace transform of unit step function is given as 1 by s. So can you tell me what will be the Laplace transform of e to the power minus at? It will be given like this. It will be given like this. Now next you have to, so it becomes e to the power minus s plus a into t. What will be its integral? Minus e to the power minus s plus a by s plus a, infinity to 0. So after you put the limits, it will be infinity will be 0 and 0 will be 1. Therefore you will get 1 by s plus. Therefore e to the power Laplace of e to the power minus at is 1 by s plus a. What will be the Laplace of e to the power at? 1 by s minus a, right. So in this way you can take any function provided it's piecewise continuous and take its Laplace transform. So here are some general functions which are given and the Laplace transforms. Like take the example of t to the power n, its Laplace transform is given by factorial n by s to the power n plus 1. Similarly sin at, cos at, sin hyperbolic, cos hyperbolic, you can take any function and take its Laplace transform, which will be very helpful in mathematical calculations. Now say you have suppose you have a Laplace of sin at. It is given by a by s square plus a square. Okay. Suppose I multiply this with e to the power minus at. Can you tell me what will be the Laplace transform? Simply by seeing from this to this. No, it will be replace s by s minus a, s plus a by s plus a whole square plus a square. Similarly, you can do for cos at or such multiplication of functions. For multiplication of functions, you can do like that. From the simple basic formulas, you can derive all the bigger ones, bigger product formulas of the functions. Now here comes the most important part or the most useful application of Laplace transform, that is converting a differential equation into an algebraic equation. Sine hyperbolic function is basically it's a kind of like we have sine functions. Similarly, hyperbolic function is also a kind of time dependent function. I exactly don't remember its curve right now, but hyperbolic का curve कैसा आता है? हाँ? माइनस एक्स हाँ ऐसे करके निकाल सकते हो. x plus e to the power minus x by 2 minus x minus e to minus a by 2j. Sin के लिए minus.
Sir, how you wrote from Laplace of sin x and then you wrote for Laplace of e to the power minus ax x.
Yes, I am actually 1 minute. साइन में 2j है ना नीचे. See the Laplace of sin ax, if you do it by the traditional formula, sine 80. If you integrate it by parts, this is by a function, you will get the value of a square by a by s square plus a square. This is the basic Laplace of sine. Okay. Now you are multiplying it by e to the power minus 80 sine 80. Now suppose you have a simple 1. Laplace of 1 is given by 1 by s, as I showed you just now. Then Laplace of e to the power 80 I showed you just now is given by 1 by s minus a. If it's plus here, it will be minus. If it's minus a, it will be plus. Okay. So simply you are just, this is just e to the power minus a2 into 1. It's okay. So this is e to the power minus a2 into sine 80. So you just adjust that s with s plus a. You can also take this thing and do it with the traditional way, but it will take a lot of time because you have 3 functions in this case, e to the minus 80, sine 80, and then e to the minus 80. You have to integrate 3 parts by parts and do it. So is your doubt solved?
Yes.
Okay. Now suppose we have a function ft whose derivative exists and whose derivative is given as f dash t. So by the traditional way, it will become f dash t into e to the power minus st dt. This is right. Now you know that the rule of integral, that is, you know this rule, integral by parts, u dv equal to uv minus v du. This is the rule. Now in this phase, take that u equal to e to the power minus st and v equal to ft. So if I apply this rule here, what will you get? Yes, you will get e to the power minus st into ft, infinity to 0, minus 0 to infinity ft into minus s into e to the power minus st. Okay. So if you put these values, e to the power minus infinity will give you 0, and when you put 0 you will get f0 minus f0. And for here, if you take s out, because this integral is over t, so s is basically a constant here. So if you take s out, you will get plus s into 0 to infinity ft e to the power minus st dt. Can you tell me what is this term? What is this term? Yes, Laplace of ft equal to fs. So basically you are getting Laplace of f dash t equal to sfs minus f naught. This is for the first derivative, like we have only f dash t. Similarly you can go for f double dash, f triple dash up to fn. Any doubts in this derivation? So if you take the Laplace of the nth derivative fn t, just like you had f dash here, you are getting sfs. So fn here, what will you get? Sn minus 1, snfs. Then we will start decreasing the powers one by one. Sn minus 1 f0 minus Sn minus 2 f dash 0. Like this we will go on until we reach the value of fn minus 1 0. This is the standard Laplace transform of an nth order derivative. Now comes the initial value function. This is a very important function, initial value theorem. This is a very important theorem, as you know, which finds many applications, like to find the initial current or initial voltage across any inductor or capacitor. You can use this one. It says that suppose we have a function, suppose you have a signal ft. So limit t tends to 0 ft. This is the initial value of the function. It's given by limit s tends to infinity s into fs. Now there are certain conditions which need to be satisfied for this theorem to hold. The one and only one condition is that the derivative should be Laplace transformable, ft should be Laplace transformable. Also, the signal should be 0 when t less than 0. Ft equal to 0. In this way, you can find the Laplace transform of any initial value of any function. Similarly, you have the final value theorem, where t tends to infinity ft, which is given by the s tends to 0 s into fs. Similarly, there are conditions like the function should be Laplace transformable and sfs should exist. Now comes the Laplace transform applied to circuit elements. You can also take the Laplace of circuit elements also. Like in this case, you have an inductor. Since the Laplace transform of a voltage will be Vt will be like Laplace of a voltage source Vt, it will be Vs. It's converted into the S domain. From time domain, it's converted into the S domain. Similarly, Laplace of any current, in this case, is given by Is. And it's a fundamental property that Laplace of the resistance remains the same. There is no change in the Laplace of the resistance. So in S domain, the circuit remains the same, only the variables is converted from time to frequency S domain. Now comes the Laplace of an inductor. Here there is certain fundamental things which need to be explained. If you have an inductor, say this is an inductor in the time domain L. When you convert into the frequency domain, the inductor becomes SL. You multiply it by S. This comes from the fundamental equation like this. You can see VL equal to L di dt, which is the normal equation. You are taking Laplace on both sides. So VLS, and I just explained that the derivative will be written like this: SL, since current is the variable here, SILS minus IL minus 0 minus. So VLS is given by LS ILS minus LIL 0 minus. So IL 0 minus, what is IL 0 minus? Initial current through the inductor. I naught, right. So here is the circuit diagram. You can see that VLS, this V, equal to LS into ILS minus LI naught. Similarly, you can convert it in the form of current. You divide it both sides by LS. ILS equal to SL, VLS by SL plus IL naught by I naught by S. So any doubts in this? कौन सी लिमिट? हाँ हाँ.
This will means teach in read in third year. Means this proof he will read in third year. He can prove, but it will take some time.
Yes, it's a big proof. Actually,
whenever you will get signal and system of your then you will able to get.
Actually, the initial value means when t tends to 0, the value of the signal which you are getting, you can get the same value as s tends to infinity. You take the Laplace transform and multiply it by s. Like I'll just give a small example. Like you have ft equal to, say you have a signal e to the power 3t. Okay. So as t tends to 0, the initial value will be what? 1. Now suppose you take the Laplace transform, it will be 1 by s minus 3. Okay. So s into fs will be s by s minus 3. S tends to infinity. Divide both sides by yes, 1 by 1 minus 3s equal to 1. So you will get both the same values in this case. These two theorems are especially helpful when you have bigger problems, like the time signal is a huge number or a huge signal, or many complex signal, or several signals are amalgamated together. In that case, these equations will prove helpful. And any doubts in this conversion in the Laplace domain of an inductor. Huh. Zero minus is basically the initial current which is flowing through the inductor, because whenever you take the Laplace of a derivative, as I explained just now. Why I didn't get you? Zero minus is because we are assuming that we are switching at the instant t equal to 0.
हम क्या कर रहे हैं 0 प्लस मतलब आप क्या बोल रहे हो स्विचिंग के बाद का एक्शन तो स्विचिंग के बाद का हमें थोड़ी अभी पता है हमको तो उसका इनिशियल बिहेवियर
Initial switching before switching.
फॉर दैट रीजन आई एम टेकिंग माइनस राइट
We are switching at t equal to 0, and before that whatever the current is flowing or the whatever charge is stored by a capacitor will not reach by Vc 0 minus or IL 0 minus. And so this is the current equation. You can see by KCL that IL will be VLS, the V is the voltage by SL, SL is the inductive reactance, and I naught by S. Okay? It's okay? Now going to the next. This is for a capacitor. For capacitor, the only change is that when you take Laplace of a capacitor, it becomes 1 by Cs. Just like inductor becomes SL, it becomes 1 by Cs. So we have the same equation, same set of equations, same process. Finally, we get this thing, this equation. IC is given by this. You can follow? Any questions? No, I think you can't follow or something. You have a question? Huh? Yes, they have given 39, 40 slides. Else if you means if I derive everything, it will take a lot of time. You can understand. You can understand that step, right? I is equal to C dV dt. हाँ.
एलिमेंट का जो नेक्स्ट स्लाइड S means वो होता है j ओमेगा
Sigma plus j.
S equal to sigma plus j omega.
Sigma 0 put कर.
Okay. Sigma is the real part. For inductor and capacitor, we consider this as
0.
Right? Because for inductor j omega and for capacitor 1 by j omega. So real
Right.
part is assuming we are 0, right?
Assuming it's an ideal inductor and ideal capacitor.
Okay.
There is no real part like resistive or anything like that.
If we are considering resistor, then there is no angle in the resistor part, only real part. So there is no S term there, right? Okay. But for inductor and capacitor, we have 90-degree lead and 90-degree lag, right? So for capacitor, we write 1 by SC, means this is providing minus 90 degree, okay? And for inductor SL,
Yes, sir.
this is providing
Plus 90
plus
degree.
90 degree, okay? That's the reason why we are taking.
Provided that we have no resistive components associated, like it's a pure inductor or pure capacitor. So this is just a summary. ZR is R, ZL SL and 1 by SC. Similarly for admittance, you can take 1 by R, 1 by SL and SC, 1 by Z. Hmm? Yes. Now this is a problem you need to solve. You need to, can you tell me what does 5ut mean? Ut is the unit step function. So what does 5ut mean? It means it basically is a
Constant into multiply
by 5 times.
ut equal to 1 by s.
5 by s.
Just convert every element into s domain and just solve by KVL KCL and you will get final answer in s domain.
What will be this capacitor's Laplace transform in S domain?
1 by 125.
Yes, into microfarad. You should take care of the microfarad also. 1 by 0.25 s into 10 power minus 6. And what will be of that current source? You know what that symbol is, right? That rhomboid symbol? That is a voltage dependent current source. See, the voltage is V0, this value is given by 3.25 into 10 power minus 3 V5. What is V5? V5 is the voltage across this capacitor. So this current will be basically depending on the voltage across the capacitor. So it's a voltage dependent current source. Okay. And that is the inductor. So if I go to the next slide. It was in milliampere, that is why I have taken in the normal ampere, 0.005 by S, V5. This is the capacitor's Laplace transform, and that's the voltage. So this is the voltage dependent current source, and that's the inductor's Laplace transform. V5 is also getting Laplace transformed into its S domain. Okay. So now can you write the KCL equation from here? You need to find V0 here. You need to find V0. Now the KCL equation what will be? 0.005 S equal to V0 V0 by 280 plus 4 into 10 power minus 6 by S plus V0 plus V0 by 0.004 S. Can you understand this equation? Kirchhoff's current law? Incoming current equal to outgoing current. Can you understand this thing? This is the voltage, this is the impedance of the path. 280 plus 4 into 10 power minus 6 by S. 10 power 6, sorry. Huh. Yes.
This one is the current incoming to that node. This one equal to, and we are considering the voltage across means every element is V0. V0. So V0 by impedance.
The total is the impedance, capacitive impedance plus
V0
inductive.
by 280 plus this one means total impedance. What will be the impedance? 280 plus equivalent this one plus V0 by that one.
0.04.
And it is already current source.
ये मतलब this is the current source, right? So from here you will see the मतलब current distribution. The current will flow from here and then it goes to this path and this path and this path. ठीक है? So it is sum. So this is 0.005 by S. So that is मतलब the voltage difference is V0 across all these branches because it is shown here, right? नहीं मतलब everything is converted in Laplace domain, right?
Everything is
So 280 is in Laplace domain and this capacitance is in Laplace
act
domain
करते हैं क्योंकि
and this
S
is in
domain में
Laplace
direct act
domain.
कर सकते हैं, क्योंकि वही तुम्हारा
So
impedance
for current through this branch will be
by
V0
direct
by
direct total
total
impedance.
impedance. The total impedance will be
उस
280
उस पाथ
plus.
का current है.
So that is what it is written.
हाँ,
there.
V0 subtract.
0.04 एस का अक्रॉस निकालना है
And
V0
here it is directly current is
वो
given
current
3.25 into 10 power minus 3 V5 and the current
by
through this
right.
branch is V0 by this impedance.
दिखा दे रुको अभी.
Next slide.
हाँ, हाँ, हाँ.
So why you can see from here, this is the current, right, from this branch. So it is getting divided into this path and this path and this path. So on this path it is V0 potential by this whole impedance, 280 plus this thing, 280 plus this thing. That is the current through this branch, V by R, right? So the current through this branch is, it is directly current, right? 3.25 into this thing. So
Current,
3.25
it's direct
into
current
this
value.
thing. And the current through this branch is potential by impedance, right? The potential difference is V0 again. So V0 by this impedance. So it is the current KCL. Incoming, the current incoming in this node is outgoing through this and this and this. So basically this. So if you solve that, you will get.
Now we have VR plus V5 will be V0 because V0 is the voltage across each branch. Sorry, I wrote it V0. It will be the current value 3.25 10 power minus 3 V5. Now since VR plus V5 you have V0. So what will be V5? You use the simple voltage division rule, 4 into 10. The V5 is the voltage across the capacitor. It will be 4 into 10 power 6 by S into V0 by the total impedance of the path. This is the voltage division rule. You are understanding, all of you? So you put this value of V5 in that equation, in that place. Bhaiya, if you go to the next. So you are putting it here. Understanding? Huh? Voltage division rule is that if you have a voltage source here and you have two resistors R1 and R2, then VR1 will be given by V into R1. Voltage across that resistor is given by V into that resistance by sum of the resistances R1 plus R2. Okay. Similarly, you have current division rule for parallel circuits. This is a current source I, R1, R2. IR1 will be given by current flowing through the opposite branch, I into R2 by R1 plus R2, right?
From there you got here V5 is equals to this total potential is V0. So this by 4 into 10 power 6 by S by total impedance,
Total,
280 plus
280
this
plus
thing into V0. Okay, from
So
there
now you are getting it. So now you get the you put in that equation the original KCL this equation V5, the value of V5,
V5 replace here.
and replace here, and then afterward, after taking V0 common, you are getting this expression V0 equal to 1.4 S plus 20,000 by S square plus 20,000 S plus 10 power 8. This is in the S domain, and this can be taken as 10,000 whole square. This is in the S domain. Now I need to convert it into the time domain. Now how will you do? You know the rule of partial fraction. K1 by S plus 10,000 whole square plus K1 by 10,000 plus K2 by K2 S 10,000. Now you are solving for K1 and K2. After you solve for K1, K2, you get the value of K1 equal to 6,000 and K2 equal to 1.4. You can solve for K1, K2 from here. Now, now you have this equation V0. Now you can when you convert into the time domain, as I said earlier, like if you have Laplace of t into e to the power 8 minus at, Laplace of t is given by 1 by s square. So it will be 1 by s plus a whole square. Laplace of t to the power n is factorial n by s to the power n minus 1. And so when you convert it back to the time domain, you will get 6,000 t e power minus 10,000 t plus 1.4. That thing is easy. S plus 1 by s plus 10,000.
Don't worry for that. You will get that in your next semester of course. You are getting the motto that why we are doing the
Laplace transform.
right?
Because from here
Our
from
purpose
S plus
was to deliver that means that why we are doing with Laplace. You will get all the inverse Laplace transform. This is not a 1 hour topic. It will take I think a semester to learn figure and system. So just our purpose was to deliver why we are using that.
To introduce you to the concept of Laplace and everything.
Right? So don't worry for that. If you are not able to get that, you will get in your next semester.
So any further questions at last?
But can you explain again what that rhombus was doing? What that rhombus was doing?
Yes. This is actually a voltage dependent current source. Like you have a normal ideal current source, which is given, whose symbol is like this. This is a normal current source. Here, what is V5? V5 is the voltage across the capacitor. So, like this is an ideal independent current source. Whatever change you make in the circuit, whatever change you may increase the resistance value, decrease the current capacitor value, anything, this source will not be affected. But if you make any change here, if you increase the capacitor value, this V5 will increase. Similarly, the current delivered by this will increase. This thing, yes, this thing is basically a voltage dependent current source. It's where the output, the current output depends on the voltage across the capacitor. Similarly, you can get current dependent voltage source, voltage dependent voltage source, current dependent current source, all such things.
But I wanted to know, sir, how it is actually reflecting in the circuit.
That's what we plan to do, but that will implement by using a BJT. So we don't have available that that voltage dependent current source. We don't have that available in the market. Like we have the voltage source we supply by giving us the voltage source, but we don't have a dependent source available in the market. So for making that we use BJT. So by introducing all these concepts, we're trying to move you towards the analog electronics. So we use BJT, that's bipolar junction transistor. By that we develop a dependent current source, and that we use in the analog circuit.
BJT, op-amp, other elements
Hmm,
will be implemented that where when input side resistance, then we will get change in other part.
Understood? Any other questions? Did you enjoy the lecture? Actually, the time allotted is too short. Else, if everything was derived and every derivation was done and everything was explained in details, it would have been more enjoyable. But anyways, have to adjust with whatever you have.
We will try from next workshop to
Hmm.
use the slide
Hmm.
so that we can deliver effectively more content.
So you people are in second year, first year, first. Achha, okay, okay. So then it will be a little bit difficult.
So first means in this semester we just that go to any network book. And solve
There are many network books available in the internet.